A bat flies into total darkness at full speed, swerves around a twig no thicker than a matchstick, and catches a moth without using its eyes. How? They use echolocation, or biological sonar. The bat sends out a sound. That sound bounces off objects, and the echo returns. From that echo, the bat builds a picture of its surroundings in real time. People often reduce echolocation to one word, ultrasound. And yes, most bats call way above the range humans can hear. But some bats use relatively lower frequencies, can produce calls that fall near or even within human hearing range. So ultrasound is not what defines echolocation. It is actually the timing and interpretation of the echo that defines the process. In bats, the call begins in the larynx, the voice box. Muscles contract, forcing air through, and the larynx vibrates to produce the pulse. Most bats emit the call through the mouth. Some, like horseshoe bats, emit it through their nose, which is why their faces have elaborate ridges called nose leaves. Those ridges shape and focus the beam. When a sound wave goes and hits multiple objects in the environment, it doesn't just bring back echoes, it brings back a complete dataset. Imagine two moths fluttering in the air. The echo from the first moth returns first. Its short time delay tells the bat it is close. The echo from the second moth arrives a fraction of a second later. Its longer delay tells the bat it is further away. Then comes direction. If an insect is to the bat's left, the echo reaches the left ear slightly before the right. If the insect is to the right, the opposite happens. Similarly, the bat can also detect whether something is above or below. Here, the shape of the outer ears becomes important. An echo from above and an echo from below return with different frequency patterns because they hit the folds of the outer ear from different angles. But position is not enough. The bat also needs a sense of movement. If an object is flying toward the bat, the returning sound waves become slightly compressed. So the echo comes back at a slightly higher frequency. But if the object is moving away, the waves become stretched and the echo returns at a slightly lower frequency. This Doppler shift helps the bat detect the motion of objects around it. And motion is only part of the picture. The bat also has to judge size. A larger object usually reflects a stronger echo than a smaller one if both are at the same distance. But in a real forest, the bat is not hearing one clean echo. It is hearing echoes from many things at once: the insect, the leaves, the branches, and the cave walls. So the bat cannot judge size from echo strength alone. It has to compare echo strength with distance, angle, and movement all together. When the target is too tiny for the cluttered surroundings, some bats adjust their calls as they fly. They may send their calls faster, make them louder, or increase the frequency slightly to target better and filter out echoes from larger, distracting objects. Different bats use different call types depending on what they need the echo to reveal. Horseshoe bats and their relatives use a long, steady call called a constant frequency or CF call, which is excellent for detecting the motion of a prey through the Doppler shift. On the other hand, many open-air hunting bats use a short, sweeping call that drops in frequency, called a frequency-modulated or FM call, which gives fine-grained detail about an object's exact shape and position. Bats are the best-known echolocators, but they are not alone. Toothed whales, including dolphins, orcas, and sperm whales, evolved echolocation independently to hunt in dark or murky water. In toothed whales, the calls are produced not in the larynx, but in specialized nasal structures and focused by a fatty forehead organ called the melon. The mechanism is convergent evolution, a similar solution to a similar survival problem, evolved separately. Echolocation is sometimes called a sixth sense, as if it were a mysterious extra faculty. It is not. It is hearing, used very precisely. It follows the same basic path as normal hearing, the ear, auditory nerve, and brain. But in a bat, evolution has tuned that path to read echoes as space, enough to dodge the twig, catch the moth, and fly on into darkness.